In this notebook we will see how to calculate various indices over multi-bands images. The indices can be used to emphasize a particular feature while reducing others. Example can be the vegetation index that allows to identify healthy vegetation or to study a specific phenomenon over time. These indices are generally calculated by a combination of different bands. For this notebook we will use Sentinel-2 images that, thanks to their 12 bands in 12 variant wavelengths, are ideal for this purpose. Let's import needed libraries. In the next cell you could find a description of each band of Sentinel mission. Since the images are small we will open them and stack in a NumPy array. This is not really efficient but good for this lesson. Let's create a plot for each band. You can observe as some bands can highlight some features instead of others. By unifying red, green and blue bands we can generate a RGB image. Before plotting RGB images we need to rescale the values between 0 and 1 since the values are floats. As you may see, the image can look dark if the pixel values are not well distributed among the possible values. We can plot the band's histograms to see the pixel distribution. We can observe how they are skewed toward 0. To improve the visual result we could apply a gamma correction. This is a technique used in image processing to adjust the brightness and contrast of an image by modifying its gamma value. This will result in less darker image. Let's replot the image after applying the correction. The image now looks much brighter. If we look to bands histograms we can observe how the distribution has changed. We will now see how to calculate some of the most important indices. Let's start with the Normalized Difference Vegetation Index, NDVI. It can be calculated as the difference between the near-infrared and red band divided by their summation as shown by the formula. This metric is used for quantifying the health and density of vegetation using sensor data. This index is particularly handy because negative values of NDVI, values approaching -1, correspond to water. Values close to 0, -0.1 to 0.1, generally correspond to barren areas of rock, sand, or snow. Low, positive values represent shrub and grassland, approximately 0.2 to 0.4, while high values indicate temperate and tropical rainforests, values approaching 1. In the plot we can observe as values closer to 1 tend to correspond to vegetation while negative values correspond to water bodies. Let's now define another index, the Soil Adjusted Vegetation Index, SAVI. It is used to correct Normalized Difference Vegetation Index, NDVI, for the influence of soil brightness in areas where vegetative cover is low. It can be calculated with the formula presented in the notebook where NIR represents pixel values from the near-infrared band. Red represents pixel values from the near-red band. L is the amount of green vegetation cover. In our case we will select 0.5. In our plot we can observe how some land pixels are darker with respect to NDVI. Let's now consider the Visible Atmospherically Resistant Index, VARI. It is a vegetation index for estimating vegetation fraction quantitatively with only the visible range of the spectrum, and it is calculated from visible bands. The Visible Atmospherically Resistant Index, VARI, is designed to emphasize vegetation in the visible portion of the spectrum, while mitigating illumination differences and atmospheric effects. Let's now plot all analyzed indices in a histogram to compare them. Let's now explore an index related to water. The Normalized Difference Water Index, NDWI. The NDWI is used to monitor changes related to water content in water bodies. As water bodies strongly absorb light invisible to infrared electromagnetic spectrum, NDWI uses green and near-infrared bands to highlight water bodies. It is sensitive to built-up land and can result in overestimation of water bodies. Index values greater than 0.5 usually correspond to water bodies. Vegetation usually corresponds to much smaller values and built-up areas to values between 0 and 0.2. Note, for this image the results are quite different from typical values expected for this index according to the terrain type. The Normalized Difference Moisture Index, NDMI, is used to determine vegetation water content and monitor droughts. It is calculated as the normalized difference between pixels values from the near-infrared band and pixels from the shortwave infrared 1 band. If you want to discover more indices, you can check ArcGIS page at the link below. We have finished this quick overview about satellite indices. In this lesson we have learnt how to combine bands of a multispectral image to calculate indices in order to obtain insights about Earth's surface. If you have enjoyed this video, I invite you to subscribe to this channel. See you soon with more videos coming.